So what we did last time, we started talking about amplifier stages using MOSFETs, right? MOSFET amplifier stages. And we started with a common source. So I'm going to review what we said last time. For the common source, the basic common source, we had the input applied to the gate and the output taken out of the drain. And you had an RD, a resistor here, V in, V out. And what we saw was that the input V in, V out behavior looked like that. So it's an inverting stage. And then when we wrote down the large signal transfer function, what we did, we basically said V out is simply VDD, this voltage, minus the voltage drop across the resistor, which is RDID. And ID was mu n C aux over 2 W over L, VGS, which is Vn minus Vt squared for a non-velocity saturated device. And as you can see, this is basically the input-output transfer characteristic for the pinch-off region, for as long as you remain in the pinch-off region. Now, if you drive this gate, if you make this voltage large enough, and this voltage is small enough, then this leaves the pinch-off region, it goes into the triad region. And if it's in the triad region, this equation does not hold. You have to write the equation for the triad and then solve that. And we didn't do it really, there was no point in doing that. And when we looked at it, we could calculate the small signal gate, basically the ratio of the variations between V in and V out, small perturbations on top of the operating point, was simply you could define it as AB is dV out to dV in, which is basically RD mu n C aux W over L V in, which is VGS, minus VT. And this thing was nothing but the GM of the transistor. So this is minus GM RD. And of course, in this equation, in the original equation, and of course the resulting equation, we don't have the channel length modulation taken into account, and therefore you don't see RO in this equation. We also did the small signal equivalent model that gave us a more accurate result. So basically we said, well, if you really take that channel length modulation into account, AV, which is defined as the ratio of V out to V in, would be minus GM RO in parallel with RD for a non-degenerate common source stage, right? And then we looked at the input and output impedances. The input impedance for this thing at low frequencies is what? Is infinity, right? Because there's no DC current flowing, at least based on the classical model, the basic model we have. Of course, we know that once the gate oxide becomes very thin, then there is a channel, there is a gate current, tunneling current as we discussed, and that could result in some sort of resistance. But for now, we say, well, that's very large. Now, the output resistance consisted of two parts. The extrinsic part, RD, and the intrinsic part, which is the impedance looking down, which is RO in this case. So the output resistance was simply R out was RO in parallel with RD, which is what you see here. So that was for the non-degenerate case. Now we said, well, in general, if we are interested in knowing the behavior of this stage when you have a resistor in the source, the general resistance of RS. Now, in practice, in many cases when you are designing MOS amplifiers, you don't use resistors a lot. And the reason is as following. Because first of all, in the basic vanilla MOS process, CMOS process, you don't get very well-controlled resistors. There are variations of the process that allow you to get resistors, but they're a little more expensive. Nowadays, a lot of MOS processes have good resistors, but some of them don't. So it's good to understand that sometimes we don't have the option of having good resistors, but nonetheless, we look at these stages as basic fundamental building blocks, because even if you have something else here to emulate the resistor, or here, as we'll see today, there are still, and from a small signal perspective, there is some resistance associated with that. And that resistance can be used in this model to predict the behavior, at least from a small signal perspective. So when I show a resistor here or there, it may be the resistance associated with some other circuitry involved in it. And we'll see some examples of that today. But now let's look at the degenerate case, which basically is when you have a source resistor, and we did that too last time. Then we looked at this stage and said, well, first of all, again, in the classic basic CMOS process, this is the way it's connected. So now the source is moving, the source is not grounded, so the VS is non-zero, so you have to worry about the body effect. And when we did that, we looked at small signal models, and what we saw is that the gain of this stage, I'm not going to redo the calculations, it's in your handout as well. The small signal gain, the ratio of the small perturbations on the output to small perturbations on the input, is simply what? Is simply minus, it was the ratio of the drain resistance, the total resistance in the drain, to the sum of the intrinsic resistance of the gate, which is Rm. Do you remember the T model? Yes, Rm between the gate and the source. Plus 1 plus pi times the extrinsic resistor, Rs, which is this resistor. Now this is somewhat similar and somewhat different from the one we had for bipolar. For bipolar it was alpha times the total resistance here divided by the total resistance there. Right? Here we don't have the alpha obviously because the drain and source current are the same at low frequencies, right? It's the same current, there's no gate current. And therefore alpha disappears. The other difference is that you have this extra correction term, which is really due to the fact that you have two transistors here. So that's the effect of the second transistor, the back gate transistor. Or the J effect if you want to think about that. Now there's another way of showing the same result, which is basically by showing this as GMRD over 1 plus chi GMRD. More similar to what the textbook uses. They're the same thing. I mean, I'm just multiplying both numerator and denominator by GM. You know that Rm is 1 over GM. Okay, so that was the gain. The input resistance again is simply, based on our model, is very large at low frequencies. And the output resistance, again, consists of two parts, the intrinsic and extrinsic parts. The extrinsic part is simply RD. It's whatever you put in there, right? So whatever you see looking down into this thing is going to be in parallel with that from a small signal perspective, because this node is ground and that node is ground too from a small signal perspective, from variational perspective. Now, the question is, what is this that you see looking down here? And we did calculate that, and what we saw was that this quantity was RO of the transistor times 1 plus GM, 1 plus chi, or 1 plus chi, GM RS. So R out, the total R out, is RD, the extrinsic part, in parallel with RO, 1 plus GM, 1 plus chi GM RD. By the way, this is the hardest Greek letter to pronounce if you want to pronounce it like Greeks. It's like something hard H and SH and a K. Alright, we call it chi. Okay, so that's basically what the output resistance is. Now, there is a difference.
RS instead of RD.
Oh, yes, thank you. This is RS.
And the top equation.
Yes, this is RS too. Yeah, this is RS. So now, one of the interesting things is that if you compare this to the case of the bipolar transistor, remember in the case of a bipolar transistor when we had a resistor in the emitter, we had RO, we had this extrinsic part which was RC, then we had RO and there was this fraction, right? It was 1 plus GMRE divided by 1 plus GMRE over beta. And then when GMRE became very large, that whole thing became just beta. Now you don't have that denominator. Because effectively your beta is infinite. Right? Your Mosfet, your beta is infinite. So, and you saw that was important in the sense that there was maximum achievable output resistance. There was a fundamental limit. No matter how many of them you put in a cascode, you could not exceed beta RO. Because even if your source resistance were infinite, still the output resistance would be beta RO. Now you don't have that here. At least in principle, at this level of abstraction, without thinking about second order effects, there is no limit to how large this can be if you make RS large. MOSFETs, I mean, maybe a 3-level cascode may have to be advantageous over a 2-level cascode, and that's true, and that's why in MOSFETs you do see sometimes designs with 3 levels of cascode if you want to get a high output resistance for a given device. And you don't see that in bipolars. You never see that. I mean, if you see it, it's somebody who doesn't understand what's going on. You can always make something, right? It may not be optimal. Just use head. Okay. So that was basically what we said. So that was the input and output resistance of the common source stage. Any questions about this so far? Okay, now the thing is that, again, these are done with resistors. But one of the things I told you is that in general, sometimes you don't have good resistors. So what if you don't have good resistors in your process technology? What kind of other loads? So let's start with the basic non-degenerate common source stage, right? The top one. And if I don't have a resistor, what can I use to emulate the effect of a resistor? There are several things I can use. Any thoughts?
Current source, voltage source.
Well, yeah. Well, an ideal current source or an ideal voltage source does not really emulate a resistor, right?
Like voltage source can be used for like smaller resistance, and current source can be used for.
Right, that's right. But then you have to get those out of something, right? So from a realistic kind of device, let's say if I were to use another transistor, there are several ways I can do it. So let me show you one way. Now, you may or may not have seen this, but this is one way of making the load. So imagine that you have an NMOS, right? And then imagine that you connect the drain and the gate of this NMOS together. Short drain and the gate. Now, this is what we call the diode-connected MOSFET. And the reason is that if you do this in a bipolar transistor, you will form a diode, right? This is a PN junction diode. But basically it's the emitter-base junction. So if you try to do something similar to that here, you can have a structure like this. Now, of course, the drain has to, and this side has to be at a higher voltage than the source, right? So let's say I connect this to the highest potential in the circuit, VDD. Right? This terminal is VDD. Now the question is, this has one terminal, let's call this V out. Now, I am going to use this as my load instead of an RD. But before I do that, let's analyze this and see what is the relationship between V out and the current through this ID. From a large signal perspective. What is it? Well, let's see. So this ID is the same as this ID, right? This is ID, this is the same current, there's no gate current. Now, first of all, to determine that relationship, what we need to do is to determine what region of operation is this transistor in. So what region is it in?
Oh, it's in pinch off.
Hmm?
It's in pinch off.
It's in pinch off, correct. Why is it in pinch off?
Because your drain source resistance will always be greater than the threshold.
I mean the voltage, right? So your VDS in this case is equal to VGS. You force them to be equal. But the condition for being in pinch off was that this VDS is greater than this minus VT. So for positive VT, this condition is always held. Because if these two were equal, then this is always smaller than that. Right? Of course, there's an implicit assumption that your VT is positive. You can't have a transistor with negative VT, although we don't often use them in circuit design, and they're not very good transistors, but you can have them. And if that's the case, then this will not be pinch off region. So it's either in the pinch off or it's off, right? Because it could be off. If V out is VD at VDD, for instance, right? What is VGS? 0, right? It's below VT. So it's either off or in pinch off. So it does not enter triode source in positive VT. So what is the relationship? So if it's in pinch off, then I know the relationship between V out and ID, right? Because I know ID is, well, those terms, mu and Cox over 2, W over L, so let's call this W2 and L2, right? W2 over L2 times VGS. But what is the VGS of this transistor? It's VDD minus V out, right? This voltage minus that voltage. So it's VDD minus V out minus VT, VGS minus VT squared. So that's my ID. So that's the relationship between V out and ID. And if I were to plot that, it would look like this. So it is ID versus V out. It's going to be up to certain points. So this is VDD. This is VDD minus VT. Up until here, the transistor is off, so the current is 0. And then it goes quadratic. Right? So it's a quadratic dependence. Quadratic looking. Fine. Now, if I use this transistor as my load, in other words, I use this as the resistor that I have before, and this becomes Vn, then this is a second transistor which could have in principle a different W and L, right? W1 over L1 in most general case. Now, what can I say about the current in that transistor? So this is the current. What can I say about this ID, which it has to be the same as that ID? That ID is simply again mu n Cox over 2 W1 over L1 VGS, which is simply Vn, right? Minus Vt squared. Now, these two have to be equal. So that's mu n Cox over 2 W2 over L2 VDD minus V out minus Vt squared. So now this is the relationship between V in and V out. I just need to solve for V out in terms of Vn, right? So let's do that. I mean, it's very simple. First of all, these guys cancel. Now, I need to take square root of both sides, so I just do this. I said W1 over L1 divided by W2 over L2. I just divide both sides by W2 over L2, and then take the square root. So it's Vn minus Vt. So that's what's left. So this term is equal to that. Now I need to make corrections. So I move V out to this side, I move this to the other side, so I get VDD minus Vt minus that to the out. So that's a large signal transfer function for this stage. This being V in and this being V out. Right? Agree? I've done nothing but to take square roots and kind of move a few terms back and forth. Now, what can you say about this kind of load in this kind of common source stage? What observations do we make? Well, an equation is an equation, right? It's not very useful in itself, unless we learn something from it. So what does it tell me? Well, first of all, what is the gain? What is the small signal gain? According to this equation. Yeah, it's this term, right? With a minus sign. Because basically it is, by definition, dB out to dB in. Right? In this case, actually, not partial. Just basic derivative. So that's AB, and that becomes square root of W1 over L1 and W2 over L2. Now, so it's the gain is determined by the ratio of the width to length ratios of these two transistors. Right? And of course, the square root. Now, is it a good thing or a bad thing? Well, depends, but let me ask you this question. Let me ask you a more specific question. Is the fact that you don't have mu and Cox in there a good thing or a bad thing? It's a good thing. Why is it a good thing?
You don't have control over that.
Right, you don't have control over that, and mu n is very temperature dependent and all those things, right? But now, mobility is a very strong function of temperature, for instance, right? Or other parameters, and it can change from one lot to another, it can change from one point of the wafer to another. But now, it's determined by really four physical dimensions. So, and not only that, it's determined by the ratio of some physical dimensions. It's not just that. So if they change by the same factor, if all of the physical dimensions all of a sudden, for some reason, your lithography or your etching process is run a little longer or a little shorter, all of them scale up or scale down by a certain amount, and the error will be much smaller when you calculate the ratio. So in that sense, it's a good thing that it does not depend on other things. And this is the way you want your circuits to be in a lot of integrated circuits. So, and we'll see this as recurrent theme, that you ideally want your circuits to be, for the gain and some of the important parameters in your circuit to depend on ratios of things that move together, as opposed to absolute values. So that, from that perspective, this is a good thing. Now, there's one more thing to be learned from this by looking at this expression, this nonlinear general large signal transfer function, the DC transfer function. Is there something in there that catches your attention, which is different from all the other nonlinear, or the transfer functions that we've derived before? Well, the square root is there, but these are design parameters, right? So this is, once you design this, these are fixed parameters, right? So that's true. I mean, you have the square root, but I mean, for some other countries have. But how about the relationship between the in and the out? The large signal one, not the small signal one.
It's linear.
It's linear, right? There's some offset and all those things, but it's linear. That's also important. Designing a linear amplifier is important, and it's potentially good thing. Because if you look at all the other expressions that you have for bipolar, we had an exponential dependence, right? For that stage, for the basic common source up there, you had a quadratic dependence between V in and V out. See that black equation up there, V out versus V in? It's a quadratic dependence. This is a linear dependence. Now, it's a good thing because if you want to amplify a signal faithfully, copy it faithfully, then you have to be able to have a linear amplifier or emulate a linear amplifier as much as you can. Because if you have no linearity like those, you amplify the basic signal, but once your signal becomes large enough, then you will have harmonic content and there will be harmonic distortion. So for instance, if you want to make audio amplifiers that are of high quality, one of the parameters that's very important is the total harmonic distortion, or THD, in an amplifier. Which basically tells me what is the energy in the harmonic content compared to the energy of the fundamental, which is the part that you're interested in. The rest, and if you listen to it, actually you hear it. Sometimes you do that intentionally. For instance, in a guitar amplifier, if you're making a pedal or something like that, that's exactly what, I mean, there are all sorts of distortions you introduce there because they make it sound richer in terms of the harmonic content in different ways. So one of the basic things that you can have in a guitar amplifier is the nonlinearity. So basically, when you go to the gain, I don't know if you've played with electric guitar amplifier or not. Does anyone play with that? Those? All right, well, good. So you basically what you have this knob that you turn, and it's called gain. So what you do, you're increasing the gain. In effect, you're making the transfer function steeper and steeper as you do that. And you hear this kind of distorted sound of the electric guitar as opposed to the kind of the smooth sound of the kind of the basic acoustic or basic string. Now, if you play with the guitar, this is something interesting you can do to see this effect very nicely. If you actually, instead of fretting the guitar is usually fretted down here, right? If you fret it on the 12th fret, which is exactly in the middle of the string, that's why you get the same note on that. So you just basically have the length of the string, which basically doubles the frequency. You get the same note. By the way, that's why it's called an octave. Doubling of frequency, which gives you the same. Anyway, so if you hit it on that, just hit it very slowly, you will hear a sound that doesn't sound like, I mean, without any amplifier, just the string, you will hear a sound that sounds very, very pure. It doesn't sound like a guitar. It sounds like a tuning fork. If you just hit it on the 12th string. Don't hit it too hard. You don't want to become excited. Too much nonlinearity. Now, if you put that into your amplifier and look at all sorts of variations, for instance, in the gain and this kind of distortions, then you see exactly what it's doing to a single tone. Because what you're putting in there is a single tone. So if you have no distortion, you will hear a single tone. But if you do have any additional distortion, you will hear a different sound. Maybe I should get my electric guitar next time here and just play with it. All sorts of distortions at some point. It's very interesting because your ear can detect all sorts of distortions. At some point, you will be able to tell what kind of distortion it is. We'll talk about other kinds of distortion, but the audio variation is good. But now, so let's imagine that, let's just assume that you don't want to introduce distortion. You want to keep it as is, and therefore you need a linear amplifier. So that's one thing. Now, let's look at this. How come it became linear? designed in such a way that they cancel each other. Now, let me tell you an interesting piece of trivia, which could be useful actually. A few days ago, I was consulting somewhere that this exact stage came handy and we started using it. Now, in that case, we didn't have kind of non-velocity saturations. They were not long channel devices. And they were not completely short channel. So this dependence was kind of, we didn't know it. In a real device, it's not exactly quadratic, right? So it's some exponent, right? But now, if you keep the two channel lengths the same, this exponent will more or less be the same. Because the same electric field falls across the same distance. Now, so you can play with the widths. Now, what happens is that even if they're not quadratic, they will cancel each other as long as they are the same. And you get this linear behavior. They wanted to have some linear amplifier with limited gain but linear amplification. And they were playing with that. And they had all sorts of problems. So well, maybe we can try this. And it did what they wanted to do. Now, but I said all sorts of good things about it, right? No, but there's no such thing as a free lunch in real life. There's always a price for it. So, what are the bad things about this?
Gain is somewhat limited.
Yeah, right? Because think about it. Let's say I want to get a gain of 10. It's not humongous, right? I mean, last time we talked about gains of tens of thousands and hundreds of thousands. A gain of 10, it means that the ratio of these two W over L's has to be quite large. So even if I don't limit myself to having the same channel length, for both devices, and let's say I can play with both of these, it means that this ratio has to be 100. So it means that I'm talking about a device that's very wide and very narrow, wide and very short, right, for the lower transistor, and another transistor that's very, has a long channel length, it's wide in that direction, and very narrow in the direction of the width, right? So it has a large, so your lower transistor should have, if you want to make it out of one finger, it will have a large W and a small L. Your upper transistor should have this should be the L, and this is the W. I mean, if you were to do that with a single finger. So this is the one transistor, this is the other transistor, this is the drain and source, that drain and source. You can see it will start looking awkward even for reasonable people. Of course, you can break it up into multiple transistors and put them in parallel. But still, you have this kind of ratio problem. So your gain is low, as you can see. Now, in this analysis, I ignore something implicitly, the way I wrote these equations. Do you have any idea what I ignored? Say again?
Suppose the current is not a constant.
What do you mean? The current is not, I'm not assuming that current is constant. I'm assuming that the same current is here and there. I'm assuming that there's no current going to the load. Right? I'm not assuming that they are constant. Right? If nothing is connected here, this current, whatever it is, and it changes in the end, will be the same as that. So that's true even when the current changes. This I is a function of the end. But still, they're the same. So that's okay, as long as my load does not draw DC current, which can be simple, right? I mean, if my next stage is another gate, from a practical perspective, I won't be drawing a lot of current, so that's not something really difficult to achieve. So that's okay. But what is the assumption that I made when I wrote this equation? It's here. The problem is here, in this equality. VT, right? What is the problem?
Assuming that the threshold voltages are the same.
Yes, that's exactly what I'm assuming, right? And why is that assumption not valid?
Depends on beyond.
Right, because for this transistor doesn't have any body effect, right? Does not have any body effect because both the gate and source are at constant potential. So the VDS from a small signal perspective does not change. However, this one has its bulk constant, but its source is moving, which is the out. So this VT is in fact a function of the out. And when I cancel these things, basically my equation will look like this. And therefore it's a more complex equation which is not exactly linear. Of course, we know that this dependence is a weak dependence. It's a square root dependence, right? So you have a linear part and a square root part, so the square root part is not going to be dominating that, but it will be a correction term, which makes it not exactly linear. Now that should show up somehow if I do a small signal analysis, because if in the small signal analysis I have, if I don't throw away my backgate transistor, right, it's the second branch. If I don't throw it away, it has to capture it. So the result has to be somehow different from the result I got here. Alright, so let's look at it. From a small signal perspective, what is my load? Let's look at the small signal equivalent of just that one transistor connected in following form. So what is it from a small signal perspective? We can do it for a transistor, right? I mean, it doesn't have to be just for the complete circuit. We can do it for different parts and reduce it to whatever its essential small signal model is, and then plug it into the rest of the circuit. Because small signal models, by definition, are linear models. So let's look at this. Let's draw the small signal model first. Let's just do the whole thing first. So just this is RO, this is RN, this is IS1, IS2, RMB. This is connected to VDD, which is ground from a small signal perspective. This is IS1, IS2. Now this node is connected to ground. This is the bulk. Now this node is connected to air. That's the gate. Where is it connected? It's ground too, right? Because it's connected to VDD. So that's also ground. So that makes it relatively simple. And this is my node of interest. So I'm interested in this impedance looking into here. So what is it? Well, do I need to worry about the current sources? This current source, what is the connection on both sides? It's really like this, right? It's shorted across, so it doesn't matter. So is this one. So I don't worry about it. Okay, so what do I see? What is the impedance looking into here? It's Rm in parallel with RMB in parallel with RO. Or you could write it as 1 over the conductance. It's Gm plus GMB plus GO, which is by definition 1 over RO. Right, that's another way of writing this. Okay, fine. Now, out of these three, which one is the least significant in this combination? RO, right? Because RO is much greater than RM and RMB, so this doesn't really matter. If I want to, and this one is okay. You know, this is chi times smaller than that. So this is, if this is RM, this is chi times RM, right? That's my definition of RM. But it's okay. Well, just I'm sorry. Yeah, this is chi times greater. The resistance is chi times greater. The conductance is chi times smaller. So effectively, to the first order, really, this is 1 over Gm. Or if you want to be a little bit more careful, you can say it's 1 over Gm plus GMB. So to a good approximation, this is really 1 over Gm plus GMB. If you want to take it into account, you can, but at the end you have to cancel everything out. So that's what I see looking up. Now, if I put the rest of my circuit down here, so that's my URD. If you want to think about it, this is my RD in that equation, in there. Right? In the basic analysis that we did up there, that's my RD. So now I can basically write my gain based on what I know already for the stage. So I don't need to redo everything. I can do it again, it's the same thing, but I can say, well, my gain is really, I know it's Gm RD in parallel with RON, let's call it, RO1, just the RO of this guy, and that will be RO2, and let's put a subscript 2 for all of these to separate these because now I have two different transistors. So this is GM1, RD. And I know RD is simply that parallel combination, so the whole gain would be GM RM2 in parallel with RMB2 in parallel with RO1 in parallel with RO2, which you can also write as minus GM1 over GM2 plus GMB2 plus GO1 plus GO2 plus GO1. And I know these two are much smaller than those. Basically, these are insignificant. So to a very good approximation, this is simply GM1 over GM2 plus GMB2. Right? You know, you can see, you also see that I kind of dropped this one and that one from the beginning, and my life would have been easier. I didn't have to carry all these unnecessary additional terms in there, because these guys are much larger than these guys. Than all this than RM. So I can drop those. So, what is my gain? Well, GM1 over GM2, right? What is GM1? What is GM? GM1 is square root of 2 mu n C ox W1 over L1. I think you've done this before. Times ID. You write it in terms of the current. Right? We did that before. That's the GM. GM2 is square root of 2 mu n C ox W2 over L2. Now they carry the same current, so it's the same ID. And this, of course, I can rewrite as, and there's another way of rewriting this, right? So it's minus GM1 over GM2 times 1 over 1 plus chi. I know this is chi times GM1. So it's basically gain, this small signal equation tells me the gain is the ratio of the two transconductances. The transconductance of the lower one, the transconductance of the upper one, with a correction factor of 1 over 1 plus chi. Because of the body effect. And now if I calculate that ratio, based on these expressions in terms of the large signal model, that's what I get. So I get 1 over 1 plus chi. Now, the ratio of these two, what is it? These terms cancel, right? It's just the ratio of square roots of W over L. So it's W1 over L1, W2 over L2. This part looks familiar, right? It's the same thing, with the minus sign. The correction term, 1 over 1 plus chi, comes in because now I've taken the body effect into account. And you can see it reduces your gain. So if your chi is 0.1 or 0.2, it reduces your gain by 10 to 20%. Okay, fine. So you can see it's hard to get reasonable gain, reasonably high gain out of this. I mean, you can get some gain, but gain is not going to be very high in this stage. Now, let's say I wanted to get more gain. I want to modify this stage somehow that I can get more gain. How do I do that? How do we do it? Well, to do that, you have to, that's why you want to do the analysis. Because the analysis allows you to see which knobs to turn or what to change to get better results. What do I need to do to get more gain based on this expression? Chi I can't change much anyway, right? It's random. So I have to increase the ratio of GM1 to GM2, right? One obvious way which we have already discovered is the ratio of W over L, but there's a limit to that. And you can see that mu and Cox is the same in both of them. As long as they are both made out of NMOSs, they are going to be the same, not going to cancel. The only parameter that's left is the current, right? But the way I've done my circuit, the current is the same too. So what if I have a way of changing the ratio of these two currents? Let me ask you this question. If I had an arbitrary choice of the currents, what do I want the current of this guy to be? Larger or small? Smaller, right? Because it's in the denominator. Basically, I want this guy to have as low a transconductance as possible. Right? Because it's in the denominator. I want the transconductance of this guy to be high, but I want the transconductance of the upper transistor to be low. I want that to be a weak transistor in a way. That's why you made it W small and L large. Now, one way to make it a weaker transistor is by reducing ID, but somehow I have to take that ID in such a way that I don't reduce the ID of this guy. Because if I just lower the ID of both of them will reduce, so the GM1 will go down by the same ratio and you will gain nothing. So I have to somehow divert some of this current away, or steal it, right? So what if I do this? I steal. Okay. So what happens? If I take a fraction of that away. So let's pick a number. Let's say I want to take, the more I take away, the less this guy will take, and therefore I will be in a better shape. So if I have this ideal current source, which I don't, but let's assume for the sake of argument that we do. Let's say I make the I steal always about 0.9 ID of this guy. If I could somehow make it copy that, right? Whatever that current is 0.9 times that, 90% of that current. What would happen to my gain? How much higher would it be? Exactly, square root of 10, right? Because this current would be 0.1 ID, therefore this will be modified, this will be multiplied by 0.1, and that's in the denominator, so it's like square root of 10. So that gain gets multiplied by square root of 10. Okay? So if it's, well, 0.9 was an arbitrary thing, right? It seems that it's working for me. So let's take it to the limit, right? I mean, we always do that. Yeah.
But with this method, though, would you be able to keep the linear performance? Because if you equate the drain currents, it doesn't come up.
No, you won't be able to keep the linear performance, but you are going to get more gain. Yeah. That's a very good observation. You will lose some of the linearity comes only if you do it the way I've shown. I mean, not only if that you do that, there are other ways of making it more linear, but if I do it this way, I will lose linearity, as you pointed out, correct? But still, I get more gain. So sometimes I care about gain without linearity. So if that's the case, then I will do this. And we'll say this is arbitrary anyway, because you can. So let's take it to the limit. Why should I stop at 0.9? Why can't I do 0.99 ID? In that case, this would be 0.01 ID. And this would be 0.01, and this would be square root of 100. What stops me from not going any further? Right? I can keep doing this forever, right? So what happens? When do I stop? What if I just get, wait, what if I just forgo this guy? What happens? This is something you're familiar with, though. This is an active load, right? I mean, in principle, if you drive, you know this is how you can get the maximum gain out of the transistor. If you load with a current source. So it reduces to something you already knew in the limit. Now, I can't make that because I don't have an ideal current source, but I can emulate an ideal current source with something else, right? I want a state that can maintain a constant current at a reasonably high output impedance. What gives me constant current? Well, a well-defined non-zero current with a high output impedance. A transistor. The drain of a transistor is relatively high impedance, right? Looking into the drain of a transistor, you see RO. So what if I just replace this with a transistor, but I need a drain here, right? So this needs to be the drain. Now, for the current to flow out of the drain, but the current also needs to flow out of the drain, the DC current. So it can't be an NPN, or I'm sorry, the NMOS. It can't be an NMOS, obviously, because in an NMOS, the current flows into the drain. It sinks current, it doesn't source current. But a PMOS is the exact opposite of it. So if I use a PFET, like that, and let's say I keep it at some constant bias that gives me the desired current, I get a relatively, this is the basic, the most simple current source I can make. The simplest current source I can make. Because basically looking into here, I see ROP, the RO of the PFET. And this is similar to what we did with the bipolars. So you can see that this stage kind of can evolve into this. Of course, it's not going to be linear anymore, as we pointed out, but it gives me more gain. So it depends on what I'm trying to achieve, because there are other ways of achieving linearity. So for instance, you can start off with a very nonlinear amplifier and apply feedback. And by doing that, you can actually make it more linear. We will see that later on when we talk about feedback. Yes?
I'm kind of confused. Like, I understand how you put the current source in there to, because that's how the transistor is acting as you increase your current larger and larger that you're pulling out. But would your large signal gain still have that
No, that form again? No, it won't.
Okay.
It will have different form.
Right, okay. I wasn't sure.
No, you're right. Actually, that's correct. That's a good observation. It won't have that form. The small signal also will have a different form. We'll do that in a second. I haven't done that yet, but yeah, it will look different.
Okay. So you're changing the behavior of the.
Correct. Yes. Again, it goes back to my kind of semi-axiomatic quest for gain. Right. For now, I'm just trying to say, well, let's see what is the maximum gain I can get out of this stage. Let's see what ways there are to play with this. And each one of them has certain advantages and disadvantages. So basically, I'm taking you through this kind of ad hoc tour of these stages to see, well, certain things are very similar to all of them. And certain things are completely different from one stage to another. But yeah, that's a good observation. So let's see what it is. Let's look at that state. Let's redraw it here and analyze it. So what I have here, I've made a stage made out of an NMOS and a PMOS. Let's say I have some sort of V-bias, and we said for now, we assume that somehow magically I have this box that generates any voltage I want in pointing in circuit, and I can maintain anything at any voltage I want. And later on, we'll see how we will do something similar to that. You can't generate any voltage you want anywhere, no variation at all, but you can make good approximations. Okay, now, so this is the V in V out. I want to determine what its behavior looks like. Now, one thing I know is that let's first determine what regions of operation I will be in. So let's try to determine the large signal transfer function, V in, V out. So when V in is 0, it's 0 input voltage. This resistor is off, right? So let's call this W1 over L1, W2 over L2. This one is off. Which region of operation is this guy? I've maintained a V-bias, which is obviously has to be above the threshold, well, below the threshold here, because it has to be lower than that. But this voltage, right, is positive enough, so I have passed the threshold, so the transistor needs to remain on, because that's a constant voltage, otherwise it will be off at all times. And there will be no current flowing within the stage for any VN. So I basically have bias to set something right? So now, what can I say about this current though? If this VN is 0. This is 0. So this transistor has a constant VGS, but it has 0 current flowing with it. What can you say about the VDS? The VDS is going to be 0, right? So, in other words, if you look at the ID versus VD, so let's do another one. So this is ID versus V out, right? So these are the ID characteristics. So for the MFET, they look like that. Right? And for the PFET, since I've fixed it at a constant bias level, it looks like that. So that's the ID versus VD curve. For the PFET, it's going to flip because it has the current coming out. And this is VDD. So when my input is 0, I'm at a 0 VGS equals 0 curve here, which is here. So the output will remain at VDD. This voltage will be 0. So I'll start off at VDD. And which region of operation am I in? For the NFET, I'm off. For the PFET, which region of operation am I in? This is the border between pinch off and triode. So this is triode, right? This guy is triode here. P in triode. And this is NMOS in the triode. So initially, the PFET is in triode, this guy is off. Okay, and I remain in VT. Once I get close to VT, this one starts turning on. When it turns on, which region of operation is it going to be in initially? Think about it. Is VDS large and VGS small, or the opposite? VDS is large and VGS is small, so I don't have a large overdrive. The transistor has a healthy VDS. It's pinch off, right? So the voltage across the drain and source is large, so I pinched off the channel. So I start off, and that means that when I start off here, I go up to the higher V in. So these are different curves for different V ins. Right? I'm initially in the pinch-off region. This is the pinch-off region. So first, so N is in pinch-off, and the P is in triode still. So I'm still here. Now, as I raise this voltage high enough, at some point the P leaves the triode. So this voltage starts dropping. So I will have a healthy voltage across here and a healthy voltage across here. So both of them, there's a region, but both of them are in pinch-off. Right? So there could be a region where both of them are in pinch-off. So and pinch-off. Okay? And then, as I keep increasing this, eventually this voltage becomes low enough and this voltage is high enough. So this goes up, this comes down, and eventually I enter this region. When I go to a larger region, I enter this region where this guy is triode and this remains in pinch-off. So now I have the opposite. So I have N, which is in triode, and I have a P, who's in pinch-off now. And remain there because that guy cannot turn off, because this voltage is fixed. That's this region. Okay? Now, where do I get the maximum gain? When both of them are in pinch-off. Right? That's when both output impedances are high, in other words. Right? Both channels are pinched off, so the impedance looking into the channel is quite large. So at that point, basically, it's this region of operation which gives me the highest gain. So that's the region I'm looking at. So from small signal perspective, if I were to analyze this, again, I could do everything from scratch, or I could realize that, okay, my gain was Gn times RO of this guy times whatever RD was. Right? So looking down, I still see RO of this guy, RON. Now, if I determine what is the impedance looking up, like I did before, I can just replace RD in that equation with that and be done with it. Fair? What is the impedance looking into the drain of a transistor in pinch-off? It's RO, right? It's the same thing. Because think about it, from a small signal perspective, this is ground. This is ground, so it's not any different from this guy. The only difference between a P-FET and an N-FET is the direction of the large signal, kind of the DC currents. One is sinking current, the other one is sourcing. So this resistance is ROP. You remember we did a similar thing with bipolars when we had the PNP and NPNs last time. So the total resistance on this node to ground, really R out, which is the output resistance, is RON in parallel with ROP. Now, let's think about it. Again, without drawing a small signal model. If this voltage perturbation is Bn, what is the current driving this node? The transconductance of this guy, right? The current is Gm Bn. It's being pulled out of that node. In other words, my gain, or V out, is going to be minus this current times this resistance. So my AV, small signal AV, is going to be minus Gmn times RON in parallel with ROP, which is consistent with that result, right? Because there I had, well, with the one that had RO. So it's GMRD in parallel with RO when I did that one, right? So my initial gain for a common source was Gm RO in parallel with R times RO in parallel with RD. Now my new RD is ROP, and this is RON. So it's the same thing. So that's my gain. Now this is a reasonably larger gain, because remember, GMRO was the maximum intrinsic gain you could get out of this stage anyway. So now instead of just one RO, I have two ROs in parallel. But since they're reasonably large, both of them, that's what I get. So let's see, what is the limit of this? Let's try to look at the small signal operation point parameters of this and determine what it looks like. So one of the interesting question is, well, first of all, what is GM for a given current? So GMN is we had when we had the channel pinched off. -1. Okay? So I'm really interested in the maximum gain of this state, which is GMRO, right, on that order of magnitude. Let's see what it is. What parameters affect the gain? So I have this times that. So I have the square root of ID here, and I have an ID in the denominator, and I have an L here, and I have an L in the denominator. So I get square root of 2 mu n C ox W times L, because of this L, canceling, half of this cancels that and the other half is remaining. And then I have divided by ID, because half of this cancels that and the remaining remains. And then I have dxd dvds. So what do I need to do to maximize my maximum achievable gain? Right? This is the maximum achievable gain for given GM and RO. But then, if I'm designing something, I can play with some of these parameters, and I want to know how I can maximize the gain.
You can increase the dimensions of the device.
Right, exactly, right? This is interesting because both W and L, increasing the width and the length of the device, or the length, will improve your gain, increase your gain. The width part is kind of clear, right? Because you increase the width of the device, you have more transconductance. It's like, if you double the width, it's like having two transistors in parallel, driving the same node. Right? So that helps. But the transconductance is only dependent on the square root. That's why there's a square root dependence. Now, how about the L? Why is L helping? Well, the reason is, go ahead. Yes, it increases your output resistance more than it reduces your transconductance. It reduces your transconductance only as a square root. But it directly, proportionally increases your R out. So it helps the product. Now this is interesting, because if you look at this parameter, what is this?
It's the gate capacitance.
That's the gate capacitance. Right? So it says, increase the gate capacitance, your gain will go up. But increase your gate capacitance, what goes down the tube? Yes, your speed. So there's a direct trade-off there. Talk about gain bandwidth product, right? Or the trade-off. Talked about that last time. There's another example. You want to increase the gain, you pay for it in speed. You want to get better speed, you have to live with a lower gain for a given process technology. Now, where does that given process technology and things come in? Well, of course, this is part of that equation. The device parameters. So if you have somehow a transistor that's made out of other materials that have higher mobility that allows you to get a higher gain for a given set of dimensions, that's possible. That's fine. Now, how about this part? This part sounds interesting, doesn't it? What does that tell you? So if I want to get higher gain, what does that tell me to do?
Lower the quiescent current.
Lower the quiescent currents, right? So it tells me that if I look at my maximum gain versus ID, the bias current, I get higher gain for lower current. Sounds initially, well, it's square root dependence, but still, it sounds initially a little bit counterintuitive. But it's okay, it's actually true, because, again, your output resistance has a linear dependence on that. So you lower it, you will have higher gain. But what do you compromise, again? Speed, right? Because you have less current to charge and discharge your capacitors. So for a given capacitors, now you have less current to play with. So it will take longer for the capacitor to charge and discharge. The other thing is drive capability. Even if you didn't have a capacitor, even if you had a resistor, you would not be able to drive as low a resistor as you could. Right? That's fine. But now there's something else that seems to be happening here. If I look at this equation, this explodes. And so at zero current, I get infinite gain, which somehow seems to violate the no free lunch principle. A lot of free lunch, actually, for nothing. So, what's wrong?
Somewhere along the way, you're violating one of
lower and lower VGS. So based on this model, what is the VGS at ID equals 0? VT, right? Which means that you're at the edge of turning on. But in reality, if my VGS is exactly VT, is my drain current exactly 0?
That would be subthreshold.
Subthreshold current, right? Now, so at some point, the fact that I've ignored the subthreshold current in conduction has resulted in an inaccuracy in this calculation. Now, we saw that in subthreshold region, the MOS transistor's behavior, the drain current dependence on VGS was what? What kind of dependence did it have? It's more of an exponential dependence, right? As opposed to the quadratic dependence. It's in your handouts, and we did that, the band diagram there. It comes back, basically goes back to the Boltzmann distribution, right? It becomes exponential in subthreshold. Now, if you have an exponential device, it's like a bipolar transistor, right? Or for an exponential device, what can you say about the GM dependence on the current? If the current is proportional to the exponent e to the voltage, the derivative would be the same thing, so it would be proportional to ID. Like bipolars, GM of a bipolar is IC over VT, right? It's proportional as opposed to proportional to square root. So this dependence does not hold anymore. You have to write a different dependence. In subthreshold, this will be proportional to ID. And hence, when multiplied by that, they completely cancel. And hence, once you get closer to subthreshold, it plateaus at a maximum level, as opposed to exploding like that. So in reality, because of the subthreshold current, it plateaus at the level. Now, there's one last thing here in this equation, which is this guy. If I were to change the variation of the XT versus VDS, what would I do? Well, if I make the depletion region that's formed in the pinch-off region smaller and smaller, right? The variations of that would be also a smaller fraction of the total channel. So one of the things I could do is to try to shrink the width of that depletion region. How do you shrink the width of the depletion region?
Or the reverse bias.
Well, for a given bias. Dopant, right? What do you do to dopants? Increase the doping concentration, right? Because we saw that the width was determined by the doping concentration. So if you increase the doping concentration, you'll get a higher intrinsic gain. That's another reason